Welcome all to my YouTube channel Shweta Gupta Chemistry Classes. As in class 12th, we are doing the second chapter solutions. So today in that we'll be discussing the topic vapor pressure of solutions of solids and liquids. That is, we are going to study about the vapor pressure of those solutions which are formed by dissolving a solid in a liquid. Like if I dissolve NaCl or glucose or urea, which are solid in liquids, then solution of solids in liquids are obtained. That is solid in liquid. So it is generally a liquid solution because it depends upon the state of the solvent. Here liquid will be present in more amount and the solid dissolved is present in the less amount. So solid will be the solute. Now if we talk about a solution in which a non-volatile solute is present. A non-volatile solute is present. You know children, what is non-volatile solute? Non-volatile solute is the one which cannot vaporize. So here this solution is formed by dissolving a solvent with a non-volatile solute. And here we have only the pure solvent. Suppose the solvent is water. Water is volatile in nature. So if you and this container is then closed. So if you heat this solution, that is, if you heat this which is a pure solvent, then at the surface all the molecules of solvent are there and these molecules of solvent are volatile in nature. So these molecules will vaporize. So as these molecules are volatile in nature, more vapors are produced, and as more vapors are produced, more will be the vapor pressure on the surface of the solvent, pure solvent. Here we are having the solvent, same solvent water, but with a non-volatile solute. So children, at the surface you will have both the non-volatile solute and the solvent. Solvent is volatile but the solute particles are non-volatile. Here you can see blue ones. These blue ones are the non-volatile solute and these black ones are the solvent molecules. So what happens children? These blue ones which are non-volatile solute molecules, they will not vaporize at all. But these solvent molecules which are volatile in nature, they will vaporize. So at the surface the number of solvent particles or the volatile solvent particles decreases. So as a result of which less vapors are formed because there is no contribution from the non-volatile solute to form vapors, but it is only the solvent molecules which contribute towards the vapor pressure. So less solvent molecules or the presence of non-volatile solute decreases the surface area of volatile solvent, thus forming less vapors and thus reducing the vapor pressure. So this is what exactly is. Now if a non-volatile solute is added, then the vapor pressure totally depends upon the solvent. And children, the vapor pressure of solution at any given temperature is lower than the vapor pressure of pure solvent at same temperature. Here the vapor pressure of this solution is less as compared to the vapor pressure of the pure solvent at the same temperature. Just now I told you the reason why it happened. So this is the reason. Why it is? Because in solid liquid solution the surface has both the solute and solvent molecules. Thus the fraction of surface covered by solvent molecules gets reduced. Thus number of solvent molecules escaping from the surface is reduced and thus the vapor pressure also decreases. Now children, The decrease in vapor pressure totally depend upon the amount of non-volatile solute, that in what quantity you have taken the non-volatile solute. It does not depends upon the nature of the non-volatile solute. It does not depends what kind of nature the non-volatile solute is having, but depends upon the amount, that in which quantity, in what quantity you have taken the non-volatile solute. So like 1 mole of sucrose is added to 1 kg of water. Again 1 mole of urea is added to 1 kg of water. The solvent is same. 1 mole of sucrose is added one time, another time 1 mole of urea is added to 1 kg of water, and that too at same temperature. So same number of moles of the non-volatile solute is added to 1 kg of water, that also at same temperature. So children, the decrease in vapor pressure of water will be nearly same because the quantity of non-volatile solute taken is same, and the decrease in vapor pressure depends totally upon the quantity of non-volatile solute. It does not depend what solute you have taken. It does not depend what is the nature of solute you have taken. That's why the vapor pressure decrease in both these cases came out to be same, because it depends upon the quantity and not upon the nature, and here the quantity is same. So the decrease in pressure is almost same. Now next one is the partial vapor pressure of each volatile component in a solution is directly proportional to vapor pressure. This you have done for Raoult's law. Na? Partial vapor pressure is directly proportional to mole fraction. This is applicable in case of this solid and liquid solution. Suppose you are taking a binary solution. Children, you know what a binary solution is? Binary solution is having two components. One is solute plus one solvent. 1 plus 1 is equals to 2. 2 is bi. So 1 solute plus 1 solvent form binary solution. Here if you add a non-volatile solute to the solvent molecules, then it is the solvent molecules only which will be present in the vapor phase, and it will be the solvent molecules only which will contribute to the vapor pressure. Just now I explained you. Non-volatile solute and solvent molecule. It is only the solvent molecules which form vapors and contribute towards the vapor pressure, and not the non-volatile solute. So children, here suppose P1 is the vapor pressure of the solvent you have taken, X1 is the mole fraction of the solvent, and P1 naught is the vapor pressure in pure state. So this is the vapor pressure of the solvent, this is the mole fraction of solvent, and this is the vapor pressure in pure state. I have told you whenever it is not P1 naught, it is in case of pure state. So it is vapor pressure in pure state. So then according to Raoult's law, we have already studied vapor pressure is directly proportional to mole fraction, children. So vapor pressure is directly proportional to mole fraction, and on removing this proportionality we get constant. So P1 is equals to P1 naught and mole fraction of component 1. So P1 is equals to P1 naught X1. Now children, if we draw a graph between the vapor pressure, if you establish a relationship between the vapor pressure and the mole fraction, vapor pressure will be on the y-axis and the mole fraction of the solvent will be on the x-axis. So on establishing a relationship between them, or on plotting a graph, what you get is a straight line. So it states that partial pressure is directly proportional to mole fraction. Whenever children you get a straight line, it is directly proportional. That is, it is what, children? Vapor pressure is directly proportional to mole fraction, and this point will be the vapor pressure of pure solvent. Okay, so this point of meeting will be the vapor pressure of pure solvent. So vapor pressure on the y-axis, mole fraction on the x-axis. You will get a straight line, and at the point of meeting here, it is a vapor pressure of pure solvent. So children, that's all for today. Thank you and have a nice day.